what I want to say here is that, well, I will just like to say thank you to all the participants, because the last days, me, Riccardo, and Matteo, we have been working very hard, and we got in touch with many of you. We tried actually to do our best to reply to you as much as possible, and it has been very wonderful experience for us. So thank you, everybody. Okay, say that we can jump into the topic of today. That is about using 3D data for your work, for your science. And what I want to say here is that it is really a shallow introduction to 3D data. We don't have the time actually to go much in deeper than that. So we will just try to do our best. After this lesson, there is the practical activities. All of you are invited, even if you didn't book for that, that's totally fine. If you was not able to install if you weren't able to install all the software needed, don't be worried. That will be mostly a demonstration. We will try to demonstrate for you many things, and you can try to replicate it later if you want, if you are interested, and so on. So I would like to start with the talk now. It's not super long, so we should stay in the times. And I would like to start with this that probably is obvious, but for many years, geologists worked basically in 2D, right? Because if you think about that, if you think about what you have been doing last days, you have been working with QGIS, and QGIS mostly works in 2 dimensions. I know that some of you at the very end were able to generate a 3D model with their map on top of that, which is of course a very nice thing to do, but we will see a little bit of how we can go farther with that, right? So this is another little warning I want to say to you. So there are many fields involved in this. So of course, if you are somebody working with robots, you are an engineer, you might then end up with totally different words, totally different keywords for the same stuff. And if you are a planetary science, probably you will work with something a little bit different also. So don't be worried if it's the first time you try to jump in this topic. You can find a lot, of course, in papers, online material, stuff like that. Just be a little bit flexible, because there are many different fields involved. So, okay, next slide. Okay, but the topics actually I would like to talk to you about are, let's say, 3. We can simplify a little bit. So the topic of 3D data is basically everything, right? Because as we said before, 3D data is whatever data you can collect from your environment, right? Because we live in a 3-dimensional world. So any data you might work with is basically 3-dimensional. And related to that, there are several different, let's say, fields, several different topics that are quite interesting for scientists. And the first one is, of course, the ability of reconstructing shapes. So going out in the field or using data coming from some spacecraft or some rovers and build 3D models in your computer. So digital representation of something you are interested in. Of course, another interesting topic is visualization, which is really important, because if you are doing science, you know that at the very end, when you want to publish a paper, you end up creating figures. Nicer they will be, better the paper can be read by your readers. And of course, something that is very important, all this 3D interest will be basically of not much application if you wouldn't try to exploit the data. So trying to collect something that you weren't able before, some scientific observation that can be provided by the 3D data. So we will see basically two different, let's say, words of this topic. And the first one, I invite you to go to this link if you want. You can do it later. I would just like to show you something because I think it is relevant. Let me just jump in my browser, and you can go at this link if you want. So what you are seeing here, it's what is called a point cloud, right? And you can see it on top here. You can see the number of the total number of points involved in this 3D model. It's like more than 200 millions of points. And my point here, sorry for the joke, my point here is that this was basically impossible just some years ago. So even imagining that you could stream such amount of data on the web directly within your web browser was something that we couldn't imagine in, let's say, 10 years ago or something like that. So keep that in mind. The field is rapidly evolving. And of course, if we just, and of course, if we just use these models because they are nice, because they look cool, of course, they are useful, but a very important point is that we want also to extract some information from that, something that is useful for making science, right? So jump back to the presentation. Let's see if I can do that. Here it is. Okay. The second topic we will see, and that we will try to do something about that in the practical later, is geological modeling. And is something that I will try to explain you what I believe it's the most important points to keep in mind about that. If you want to try and you are, let's say, a Python user, you can try to run this command. And what you will see is something like this. Okay, so this is basically a collection of 3D data. This is just an example. It's not something planetary. It's a model of a geothermal reservoir, but I would like to introduce 3D models like this because it makes you understand exactly what we are talking about. So giving to geological structures, to geological features, a three-dimensional representation, it is not only a way to collect all your information. So for example, here you can see the drillings that have been made in this site. So the well bores, you can see a surface here, the white one, which is the top of a granite intrusion that then it outcrops in the mountains here. Then you can find also other kind of data like the temperature. So the surfaces you see here are basically the temperature represent the temperature gradient in this location. And an important point is that if you do this kind of 3D modeling, you are not just doing that for looking at the data in 3D, which is nice, of course, but also to be able to do prediction about that data. And we will see that later. Jump back to the presentation. Here we are. Okay, so now we have a little bit of theory. It's nothing really to be worried about. I just want to drop for you some ideas that I found in the past, at least for me. I found them very useful. So there are some basic terminology, some basic theory that if you find yourself really interested in that, you can use this information to, let's say, Google it and search more and more information. So of course, when we talk about 3D data, we need to talk about the real primitive of 3D data, which are the points. Depending from the field you come from, you can call them vertices or points. And of course, you know that for telling somebody the position of a point in space, you need three values. So there is some vector representation here of the points. And if you have more than 1 point, you start collecting a lot of points, like in the model of that mountain we have seen before. You start talking about point clouds, which are just basically list of points with no specific ordering. So, of course, if you are interested in 3D data, take your time and get out your linear algebra school books, because there is a little bit of that involved. Just as an example, if you are dealing with different transformation like translations and rotation in space of the points, it is an example in 2 dimension, you need to be pretty aware of what you're doing and the matrix representation of this transformation. And in particular, there is a useful representation. I'm dropping these keywords for you, homogeneous coordinates. You can then try to search it if you are interested into that. And I'm telling you that because later in the practical, we will see some transformation metrics in Cloud Compare. I would just like to you to have an idea. It's a way of, let's say, embedding both rotation and translation in just one transformation matrix. And it is really relevant to the next slide that I would like to just, let's say, just for you to have a little bit of understanding. So there is a lot of projective geometry involved when you work with 3D data, both in the reconstruction of the shapes. So let's say starting with imagery and trying to create your own 3D model, or if you are doing also the other way around, for example, you have a 3D model and you want to create a new image representing your 3D model to put in your paper. And also for scientific purposes. So for example, you might have an image taken from a different an instrument, and of course you need to know everything about the instruments that took that image for being able to correctly characterize the relationship in between the three-dimensional world and the flat image. So this is, in this example, I just wanted to show you that, of course, when you have different cameras looking at the same object, as you well know, the images coming from those different cameras are different, of course. But an important point is that, of course, the world is in 3 dimensions and images are just in 2 dimensions. So there is a lot going on in terms of mathematics for handling the projections from 3D to 2D and in the other direction too. So if you want to get into that, of course, I should suggest you to get more in deep in these topics, which are very useful and important. So as an example, if we wanted to establish correctly the relationship between the 3D world and a picture we have, we need a lot of parameters. And some of them really depends on the position and the orientation of your instruments taking that image that is collecting the pictures of your camera, basically. And of course, you have a lot of parameters that are related to the camera itself. So no camera is equal to another one. And of course, they might have different focal lengths, different internal parameters, different distortion, optical distortion, different sensors. And you need to know all that information to work properly with this kind of data. Of course, there are sources for that kind of information. And I would like to recommend you to have a look at what SPICE kernels are. I'm pretty sure some of you already know that. But as an example here, I would like to show that they are basically used to query databases of navigation information and other information from missions. For example, asking what was the position of a given spacecraft at a given time in a given let's say, reference frame, right? So in this example, I was asking, give me the position of the Rosetta spacecraft at the time t in the reference frames of the 67P comet, right? And the same apply, for example, for the rotation. You can ask the orientation of a specific camera in respect to a specific reference frame, the one of the 67P comet here, at a given time. And that is really important. I know that many of you might be working with, let's say, tools that are not transparent in there because they might be doing this service for you, but getting an understanding of how SPICE kernels work, I believe it is really useful. So just we can just go back. I would like to stress a little bit basically how three-dimensional data is stored, both in file formats and in your computer, because at the very end, the usefulness of 3D data on whatever digital data you are working with is because they are represented digitally in your computer, and you can do computation on that, and you can transform that data in something that is, for example, scientifically relevant or useful for your research. So we started with points, the real primitives. If you have a list of points, for example, and you order them in the right way, you can easily create lines, right? So let's say we have a list of points, we start from the first one, then we have another one, and so on. So we just need, it's not really a sorted list, it's an ordered list, right? So we just need to put them in the right order to represent lines. Of course, there is something more complex, and I guess here my presentation got a little bit mixed up. That's not a big problem. So many of you, when working with 3D models, of course, I guess most of you know what a DM is. It's a special kind of representation. But in the general sense, and for what we will be seeing in the practical later, I would like to introduce you triangulated surfaces, and we will try to explore them, look how they are put together. They are also called meshes very often, or TIN, if you come, let's say, from the ArcGIS domain or something like that. The idea is that we need to provide a list of points like this one. So we have 0.0, 0.1, 0.2, exactly like we have seen before. And let's say if we wanted to define an age for this three-dimensional object here, we just need to say which point is connected to the next one, right? So for each edge, we need 2 points connected together, and we need a way to specify that. And for surfaces, we need to create faces that can actually represent surfaces. In this case, we have triangular faces. And the way this kind of information is stored in your computer, there are many ways to do that, but as the simplest one we can think about is just collecting the list of points, assigning them an ID, let's say 0.0, 0.1, 0.2, and so on, and then explicitly listing for each triangular face which points are connected together. So let's see an example. For this triangular face, the first one, we have 0.0, 0.1, and 0.2. So let's say 0.0, 0.1, and 0.2. So this would represent the phase T, the T0. This would represent phase T1, that I'm sorry for the numbers messed up. This will be T1, so vertex 1, vertex 2, vertex 4. And in the practicals, I will try to open up some files representing meshes so we can have a look that actually the representation the computer is making internally is something like this. And you might believe that this is not really something so much interesting because of course, I guess most of you can work with can, of course, work with a lot of software that are pretty advanced, and you might never be in the need to understand this. But I really believe this is really important to have at least an intuitive understanding of this information. So let's see an example. We can list the points here, for example. We can list the points. We can attribute for each point a different ID. So we have 0.0, 0.1, 0.3, 0.4, and so on. And to represent this shape, this shape model here, we just need to provide a list of triangles, right? So we have the first triangle that is built by connecting 0.2, 0.1, 0.3 using their indices. But I'm telling you this because we are not actually restricted to using triangles. So you might end up having models that are not built like that. So you might be expecting triangles, and you end up instead with little surfaces that are square-like. Of course, the principle is basically the same. You still need a list of vertices, and you can explicitly say which face is, which point is connected to which other one to create each face. Okay, and if you followed me until now, the idea is that this way of seeing your data can be extended to anything, basically anything that you might want to represent in 3 dimensions, right? Or also in 2 dimensions. So for example, if you are doing simulation, for example, finite elements or computation like that, you might need to use volumetric meshes, but the idea is basically the same. Just we don't need to specify triangles, we don't need to specify quads like before, but we need to specify tetrahedrons. So your data set will be composed by a list of points and an ordered indexes set of tetrahedrons, each representing a small portion of the volume. And as we said before, of course, you have all the possibilities in the world. And this is why I'm telling you this, because it's a very nice, good, and sane way to keep ordered your information when you are working with complex data. And of course, you can create any kind of geometry in this way. And you see some special cases, like this one, for example, that's a pixel. Because of course, also images can be modeled with this idea of data. So each pixel is a data point, and basically each pixel is connected to the nearest one on top, one on the bottom, and around that. You can transpose this same idea in 3D, and they are often called voxels. So the term voxel is mostly used for this, let's say, little cubes representation of 3D volumes, which, by the way, are really good with your computer because they can be represented as very simple matrices, so they does not need much space on your memory. And the next point, so we have seen now that starting from points, we can try to connect them explicitly. So let's say, given for each triangle, we want to create the list of points that we need to connect together, or implicitly. So let's say, like in an image, you know that a given image have a given pixel size in the 2 dimension, or if you are dealing with three dimensions of voxels, you need to specify, of course, the size of the 3 different dimensions, but you don't need to specify the complete list of each point. The next big topic that is interesting is that when we are dealing with this kind of representation, of course, we can also add data to our models. And this is really important because in science, we might have a lot of data that relates to specific locations in space, and we want that information to be tightly connected with the three-dimensional representation. Of course, this data can be vector-like, so you can have 3D vectors, for example, like if you are expressing gravity or a surface normal or something like that. Then they can be scalars, and we will see later in Cloud Compare a little bit of how the data is connected, which points or meshes. And importantly, this data can be connected either on the points. So you have your list of points, and nearby that you can put a little number with the scalar, or can be connected with the faces, right? So the what are called here cells, but basically the triangles of your mesh, right? Okay, so this is an example of properties connected to a 3D model. And so we have this little model of Comet 67P, where I've been computing gravitational potential and the gravity acceleration. So gravity, you know, is a vector. And for each point of the 3D model, we associated the connected vector of the gravity in that location. And of course, the potential, which instead is a scalar value, and which is represented here as a color bar, basically. So you have low potential and higher potential on the surface. And let's say vectors, once you have this kind of representation, it's very easy. You can find a lot of software that can do that to create nice representation of your data. And that is very important for the scientific investigation you are dealing with. Okay, just the last keyword I just want to drop there is textures, because you probably know what they are. You already heard about textures. Long story short, is a nice way to put images on top of 3D models. So you have a 3D model here at the bottom. You have an image that might come from some totally different investigation, and you can stitch that image in the right way on top of the 3D model to have something that was previously just two-dimensional, have that information in 3D. I would just like to briefly, I'm not sure I'll be able to explain it easily, but how they work. So the keyword here is UV mapping, which is a technique to express the mapping existing between the 3D model here and the corresponding image. So what happens internally is that for each vertex of your 3D model, and what is called an UV coordinates is also stored for your 3D data. UV coordinates correspond to a reference frame that relates to the pixels of your image you want to put on the 3D model. It's a normalized reference frame. So let's say you have a coordinate 0, 0 here, coordinate 1, 0, and so on here. And for each vertex, for each of your vertices, you need to express the UV coordinates. And these are very common. We will try to dissect a file later, opening it up in a text editor and look for UV coordinates, which are very important to understand, especially if you are working with meshes and photogrammetry. Okay, of course, we need to say something about how 3D models are created in first place. Of course, we could talk about that all day long, probably, but I see that makes sense to see two big different ways of doing that. And the first one is using laser ranging, and the second one is using basically pictures. So the idea here is that Either you gather two or more pictures of the same object from as seen from different point of views. Let's say what they are called stereocouples of pictures. Or there is an interesting technique which is photoclinometry, or also known as shape from shadow. So basically, laser ranging uses laser pulse. So there is a big laser diode on your spacecraft or on your, let's say, device. And the laser is pulse, and then the time of flight of the laser pulse, the time needed for the light to reach the surface, in this case of Mars, to reach the surface and then come back is used to compute together with knowing the speed of light, basically, the distance. On top of that, you of course need a very precise positioning for your spacecraft, for example, or your device, which is taking these kind of measurements. You need a very precise positioning and orientation for that to work. Because of course, each measurement, keep in mind, is just a measure of distance. And you to translate that information into a three-dimensional point and then possibly into a DM like this one, you need a lot of navigation data. The second method is photogrammetry. I guess all of you know a little bit about that, but the idea is that we use different images taken from different point of views, and we process them. And at the very end, we get something like this, right? So a 3D model of whatever was the object in the pictures. It might look like easy. It is not, because a lot of problems they might occur. In particular, also in this case, we need extra precision in all the camera parameters, in every camera parameter. And this is often done by bundle adjustment of your data. This is just to let you know a keyword you might look for. So basically, to improve the quality of a model, it's very important to perform this bundle adjustment. That is basically a minimization process that try to minimize the reprojection error on the images for key points on the image. So the last method, the shape from shading, it's not very super useful by its own, but it's most of the time you can find it associated with, let's say, a way of improving something, a DM that already exists. So this example came from the ESP guidebook. And you basically start from a rough 3D model, a rough DM. You can use one. In this case, you just need, possibly you can do that also with just one image. And what you are doing here is that you are using the information which is embedded into the shadows that you can see. So you are basically using photometric information from your images to refine and produce a better DM. Okay, so the real topic here is 3D geological modeling. And what I would like to do with you now is try to dissect this definition, which I found that is really appropriate for 3D geological modeling. So of course they are computer techniques. So we are talking about using computers. So digital representation of three-dimensional objects, which involves, as I said before, a lot of different fields, computer graphics, rendering and stuff like that. But it is useful for the geological interpretation. So the idea here is that you use those techniques to improve the interpretation you can do about a geological body. And it's really important because it makes it possible to perform also predictions. So the statistical and geostatistical part is really important because doing prediction is, I mean, science is all about doing predictions. So you do your prediction, and then you try to verify whether you can explain something, right? And you can verify your theory. So that is a very important keyword. Graphical visualization, we already said that is of course important in any science. But the last 2 points are inaccessible geological conditions, which of course I'm pretty sure for planetary science looks promising, and especially from limited information. So there is no field like in planetary science where information is limited, and you have to just try to do your best with the information you have. Okay, long story short is basically the representation of geological geometries like layers, fracture, faults, but can be also mineralization, uh, oil presence in a three-dimensional digital way. Okay, just to clarify, basically there might be some confusion about that. When we talk about 3D geological modeling, we are not really talking about dynamical modeling, or let's say geodynamical modeling, which is more connected with the modeling of the processes that evolve in time. But 3D geological models, of course, can be changed in time and can also account for changes that happen during the time, but they are pretty static. So the first goal is just to have a static representation of your geological objects. And it is also not necessarily connected with the shape reconstructions we have seen before, like photogrammetry, shape from shadow, or other techniques. But of course, they are connected and they are related, because of course we need 3D shape models to start our 3D geological models. And we need 3D geological model if we ever wanted to perform dynamical modeling of a very specific process we are studying. And of course, these different fields can talk to each other and can provide interesting feedbacks in both in all the directions. Okay, so a first point that is important to keep in mind is that we need to always choose, let's say, wisely what we want to represent in a 3D context. And of course, it depends on the application. You have been, some of you have been doing mapping the last days, and you have seen the difference between mapping, let's say, performing a morphological map, a stratigraphic map, or spectral mapping. Of course, different representation of the information are always useful, but they depends what you are looking for. So my point here is that, for example, 3D models are heavily used in the mining industry, and they are used, for example, to represent and predict ore grades. So they want to know where to drill to get the best, where to excavate, basically, to get the best recovery of the raw material they are collecting. So anyway, the building blocks are always the same. We could talk about geological units. Of course, if you we might have different flavors of that depending on what kind of representation we are doing. But in general, to simplify, we can say that there are volumes which has some kind of characteristics. We distinguish them from other portion of that same geological body. As we said before, it depends on what you are doing. So you might be interested in the lithology, fluid permeability, ore grade, and of course, then you are limited by the information you got, right? Because it makes no sense to define your units on the basis of some information which you don't have. Okay, so just some silly examples to have an idea what we are talking about. Let's say we have a stratigraphic sequence. I'm just telling this because some of you might not be geologists. So it's just a pile of rocks formed in tabular bodies, one on top of each other. And a three-dimensional representation we could try to give to that is something like this, where we have different units. So in this case, we have 6 different units that are represented with different colors. And of course, the attitude of those geometries might vary in space, might be different. So to model something like this is not very difficult, but of course, then naturally, you can find more complex things like folds. Those are the building blocks that you would like to put in your model. So if you have folds, folds might help you. Of course, they will help you in understanding the geological history of the body you are studying. So giving them a nice three-dimensional representation will give you a lot of information about the orientation of the stress field the body has been subjected to. So, of course, falls, fractures, any other kind of discontinuity in your model might require special attention, and of course are useful again to understand geological history of your geological investigation. Okay, so let's see. I will try to be very simple here. What methods we can use to create these kind of models. So the idea is that we start with limited data, if you remember that definition of geological modeling. And basically what you want to create is something like this, right? But it might be different in representation. So here I like to put this kind of block representation, but of course the problem here is how we estimate surfaces, continuous surfaces, to create this kind of representation. Okay, this is a diagram coming from a paper that was trying to summarize all the data that can be used in 3D geological modeling on Earth. And of course, if you try to read it, you will see that there are no such data available for many planetary bodies, but some of them, of course, are, like, for example, geological maps, geological cross-section. You saw the last day how to create them, and possibly you should also consider trying to get a good understanding on how to create geological cross-sections. So we can do that. There is some data we can use for creating 3D models on planetary bodies, but of course there is not much. And so let's have a look at the data. Of course, you know, geological maps. Geological maps are very good, the first resource for creating any 3D model, because they summarize everything that is known for the surface geology. And of course, you can also find geological cross-sections like this one, which indeed are basically trying to fill the gap between the map and the 3D world. So trying to represent along just one section what is below the surface. And basically what we are trying to do with 3D geological modeling is to extend this kind of trick to the whole region we are studying. So we can have a very consistent model everywhere. So just to prove you that geological maps truly represent something that is in 3D. And you can see the three different little silly models we have seen before, with just planar sequence, with some folding and with a fault in between them. And if you look at the map representation, the top view of this model, you can see that the contacts between the different units on the map, they change shape. They are quite similar, but they change shape. And we can use this information as the first information we can put to create a 3D model. Okay, as we said, maps are very interesting as the first data to use, but we are also looking for subsurface data. On the Earth, we have plenty of really good seismic cubes that are mainly used by oil companies, basically to probe the underground. using basically seismic reflectors, like this one you can see here in this data cube. And they can use that information to create very detailed 3D geological models of the subsurface. Of course, they can come also in the shape of just sections that you can put together in 3D space. For what is concerned to planetary science, the most similar thing we can imagine are data from Charade and Mars's instruments. So here you see the northern polar caps of on Mars, and you can see here the this a little, it's not really clear, but each line of this represents the coverage of Charade instruments on the surface of Mars. So there is a little portion of the polar caps that has never been investigated to the tilt of the orbit of the orbiter. But of course, most of the polar caps have been probed with this underground probing radar system. And later in the practical, we will have Giacomo that will tell something about the this kind of instruments, and we show us a couple of examples of data sets that come. Just for your reference, this is the typical image you get out of the polar cap, right? So this top surface is the top of the northern polar cap, something like this. And the bottom, you can also see the bedrock at the bottom where basically the ice is laying, right? So this kind of information looks 3D if you look at the data here, but of course you can use navigation information of your orbiter to place them in the three-dimensional space. And what we will be trying to do later with the practical is to import some of those same sections actually in a software to visualize them. And we will try to perform a very simple, let's say, interpretation of the data. So you can have a feeling of what it might look like to work with this kind of data. Of course, there are other instruments which are providing data from the underground you can use. So here is an example from the U2 rover on the moon that had a GPR mounted on the rover. So also in this case, the kind of images you end up with are, they look like flat images, and you can use those to do your interpretation. But of course, you can also merge that information with navigation data of the rover and then create 3D models out of them. At this link, you can find all the processing that we have been doing for creating this example. That was something we tried to do within the framework of the PlanMap project. So let's say you have basically two different approaches. People doing three-dimensional geological modeling often say there are those two approaches, but I mean they can work also together. They are not exclusive one of the other. But to make you understanding a little bit, let's see an example where we have this kind of structure, so a stratigraphic sequence that has been folded. So the problem here that we are trying to solve is to how we estimate those kind of surfaces. So we will see very, very briefly in 2D how it works, more or less. So this is the kind of model we want to end up. Of course, this is two-dimensional for simplicity, but the same apply in three dimension. And the point is that we have been given a very limited information about the surfaces we want to create. Of course, you can very easily try to connect the dots, and that will be basically what will be called explicit creation of the surface. It is not that simple. You can use different methods to do that, but just to make you a little bit understanding what we are dealing with. So another interesting approach is the implicit creation of surfaces. Okay, follow me just one moment because I forget to put some material on this slide. But the idea is that if you have a volume in space or on the surface, like in this case, what we could be trying to do is to define a function of that space. So a function of x and y in this case, or just x, y, and z in three dimension. It should be a scalar value function. In this case, we are representing that function with different colors. So you see different colors correspond to a different number, basically. And the approach here is that as soon as we define that function, we can use contour values, contour surfaces extracted from that scalar field. So basically, each surface will be connected to a specific value. This is a very useful approach to use for stratigraphy in particular, but it can be used. And I will just skip the slides because we are a little bit late, maybe. Let me see. Okay, no, we can talk about this. Of course, this approach, it might require you to have some, let's say, adaptability to the data you have, and sometimes you cannot have the data you would like to. So sometimes you need to transform your data into something that is mathematically usable for you. So let's summarize this about the implicit generation of surfaces. What we want to do is, of course, define a function f that is function of the space, basically, of x, y, z. And then we need to provide some different types of constraint for that surface. So like saying, okay, the surface in this point is oriented like this, and the surface must pass exactly for that point in space. And these kind of constraints are then used to solve for the surfaces we are trying to generate. So of course you can have of contact structural gradient constraints. So like saying my surface must have this orientation in that given point, or on contact or equality constraints. So my function should correspond to a specific given number at that point. Okay, just to summarize this method, basically you define a real valued function f of x, y, z. Ideally, the shape of f comes with whatever you know about the problem. That is not normally possible, and we will see just briefly a solution for that. And then you have to transform geological observation into a list of constraints that make sense to solve for the parameters of f. And I will just show an example that probably intuitively that will just be easier to understand. If you are looking for which kind of function we are using normally, have a look at Kriging or RBF, radial basis function, which are really flexible and can be used to create any kind of representation of the surfaces. For the ones of you who love math, this is the mathematical expression for an interpolator based on radial basis function. But intuitively, the idea is that you basically use some kind of basis, in this case, a Gaussian curve, and you can translate it, you can scale it, and then use all of them together to create a complex surface, which would be this top surface here. And as I said, you basically can create very complex surfaces, and all the points you see here are the constraint, basically. So you have constraints that you can use to say, okay, the surface here must be oriented like this, and the surface here, for example, must have a different orientation. And this principle is common to basically any software you might try to put your hands on for 3D geological model. So I will just end with an example. I would like to ask Riccardo if we are in time. How much time do we have?
So I think, yeah, we are.
Okay. So this is an example okay, thank you, Riccardo. This is an example we really loved because Matteo was really involved from the beginning into the understanding of the inner structure of Comet 67P. You know about the Rosetta mission that sent an orbiter around, not really an orbiter, probably I should say, a spacecraft to navigate in the space around Comet 67P. And we had those kind of beautiful images, really beautiful images. The comet is composed by two lobes. One is bigger and the other one is smaller. So we can call them the small lobe and the big lobe. And they are connected by a little bridge of material connecting them. And basically, what Matteo discovered on that comet is that the comet is layered, and this is a very geological observation to make and can be made basically on the basis of the morphology we can see on the surface. And I will show you this little rendering of the 3D model of the comet. So basically you have very extended cliffs like this one I marked in yellow. They are all over the comet and they are stacked one on top of each other. So if you cut the 3D model with a section in this direction, you end up with something like this, like the image you see at right. So you have a series of terraces going up and then coming back again. So if you try to perform your geological interpretation, you might end up saying, oh, looks like this surface travel within the body and then it came out on the other side. So that is the whole idea for a layered comet. So this lead Matteo to think about a conceptual model for this kind of geological observation. And this is something that I would like to stress. We cannot do good 3D geological modeling if we don't have a good conceptual model for what we are trying to represent, because of course deciding which functions we are going to use to create the model, deciding what degree of freedom we are going to leave to the model, how much we can trust to extrapolate the data is very important, because if we are going to use the model to perform prediction, it's truly really important. And this is needed to be taken into account. So the idea here is that if you cut your comet with different section and you try to do the same exercise we have been doing before in the previous slide, you might end up with some section like this, right? So the idea is that the comet might be layered in a very similar way to an onion where you get out some little pieces here and there, and you end up by clearly seeing the layering because you create this kind of terraces, right? So terraces, one cliff, another terrace, and another cliff, and so on. Okay, so let's see the problem there might be with this approach. Of course, you can create new sections. You can work in 2D, like on paper by hand. That's totally fine. But if in the next step is to put the data in their actual 3D space, if you do this exercise, and you might find something really not really surprising. That is, well, each section was created independently from another, and even if you try to do your best, you might be found that it's very difficult to create all sections in a way that they are consistent. So this is a very interesting check to perform. If you create many geological cross sections, you put together them, and they must correspond one to each other. So in this example, you see that if you start here following this stratigraphic horizon, you can follow it in another section. But what happens is that if you follow it in the next one, you end up with troubles, right? With some troubles because they should correspond. So the way to solve that is to apply three-dimensional geological modeling. And the idea here is that very simply, we can try to sit down and think about a numerical model that can be used to represent the, let me go back. We need a model that is useful to represent something that looks like this. Of course, when we are dealing with models, we must account for some approximation, right? We need to understand that whenever we are digitizing some information in our computer, that is not the reality anymore, right? It's just a representation we're doing of the data, and it's good to understand that there is some approximation involved. So the simplest example of numerical model we could imagine might be something like that. So a series of spheres all centered in one given point. So you need just one point, which will be the center of your spherical shells. You just need 3 parameters to define that. This is a 2-dimensional representation just for simplicity. And of course, you can create as many shells as you want. So the idea here is to create an implicit model. So we say the function f is function of the position in space, and its only parameter is the center. We want to the spheres to be centered in. And with this definition, you see that you can trace any contour of your scalar field, right? So you can say, okay, let's have a look at fp equal f1 might correspond to a given spherical shell. This might look so silly and simple, but the same principle apply whenever you use more complex f functions. So you can find any kind of different interpolators you might use that might be more complex than this. Okay, so we can try to improve it a little bit. Let's say even just spheres is not really what we want because they are not very flexible to represent the geometries. So we could try saying, okay, forget the sphere. We can try with ellipsoids, right? So in this case, the idea is that let's look whether we can represent this layering of the lobes of a comet with different ellipsoidal shell. So you work at the math and you end up with a function that looks like something like this, which is not really important to get a full understanding. But of course, you have a scalar field in space, which is function of the position. So it's basically defined everywhere, basically, almost everywhere. And the number of parameters you need to define a model like this in 3 dimensions are just those. So you have the center of your ellipsoid, the axial ratio between the 2 axes of the ellipsoid, and of course you need to try to orient your ellipsoid in space, so giving the information about the rotation. And okay, then what we need to do, okay, we defined the function, so this f function, but we don't know the parameters. So this happens independently in any kind of modeling you're trying to do, geometrical modeling of this kind you're trying to do. You need to provide constraint for your model. So you provide observation to your model, you try to fit your model to your data, and you try to obtain the best model you can for the information you are provided. So in the case of the comet, we decided to use the orientation of each terrace. As you remember before, each terrace seemed to represent a specific stratigraphic surface, so an horizon, we could call it stratigraphic horizon or something like that. So the only information we can get out of this model is the orientation of the model at that specific location. So in this picture, it is represented by the little arrows, right? So the arrow represents the orientation of the terraces on the wall comet body. So this is a good example of having a 3D model. So the 3D model of this comet was created by someone else, and I exploited it to obtain some useful information for my scientific case, right? Then, of course, if you want to find the best fitting model, you have to define some metric that allows you to tell how good is your model with the current configuration, and you can try to minimize the errors basically to get the best model you can for your scientific case. Of course, then you can try to perform visualization. And this is crucial because you can create any model, but then you need to see whether your model actually corresponds to features on the surface. So validation, it's incredibly important. So these are rendering of the cometary body, and in red, I've shaded all the cliffs. So let's say the vertical walls on the cometary body. And you see the cliffs that tend to be oriented like in this direction or here in this direction, right? You can find them here in this direction. So the idea is that if our model is good, we are able to correctly reproduce this orientation, right? So we can have a look at those lines which represent the orientation predicted by the model, and we can try to look for discrepancies that might say something about our model not being so good in some places. This is also an example of what you can try to achieve by using all the information you are provided. So for example, here we have a real picture of Comet 67P taken by a camera on board Rosetta. On top of that, I produced a three-dimensional representation of the lines. And I also was able to correctly orient the 3D model in this rendering here to look exactly like the image. So how to do that? You already know that. If you go back some slides, you need SPICE kernels. You need the information of the navigation data to know where the camera was pointing when a specific picture was taken. And this is very useful to know and to be able to get that kind of information. So at this point, you have a very consistent model. You have basically two different models for each of the lobes. You can create any number of sections. And this time, whatever section you take, they will be perfectly match each other. You can compare that with what could be done by hand. And of course, they are different. But an important point is that if you're doing that, the effort of creating a model and fitting the model to the observation, obtaining some data back, doing prediction of your layer orientation, an extra effort will be to produce statistical parameters for your model. So a way of saying how much confident we can be about the model, right? And that should be done for the parameters of the model and so on. So just very fast, the idea is that then you can use the model to perform prediction, even if it's an approximation. But if you have done your computation right, in the right way, you have all the statistical information about your model, you can also try to do prediction. So like in this case, thanks to the model, we can predict where material is missing, because we can play this little trick and say, oh, okay, some layers are missing now, but they must have been there at the very beginning. So we can try to complete basically the geometry just by following what we know. So extrapolating the information we know on the surface to extend it where we don't know anything about that. So inside and outside the 3D model. And if you do this little trick, you end up with estimates, for example, that in the case of the big lobe, we lost somewhere between, let's say, the 50% of the initial volume of the cometary body. In the case of the small lobe, we are around the 70% of the initial volume. So that is just to tell you an example of using 3D data, 3D models all together to, at the very end, give a prediction about some science topic you might be interested in. Okay, then you may say, okay, that model is boring. It's so simple, and you already showed us that is good, but not so perfect. And my point here is just okay, but keep in mind the same principles apply with more complex interpolators. So you might define your function f to be very complex, very with a large number of parameters, but this basically doesn't change the approach. You still have to use your observation, you have to fit your model, but of course you can have very much more detailed 3D model, much more flexible 3D model, much more complex layering, more, a more complex model for your layers. And this is really important because if you do that, you might end up seeing something like this, that the layers are all but perfect ellipsoid, and that is perfectly fine. We started off with a rough approximation, and we can end up with a better approximation. So you may say, yes, but what is telling us this kind of information? Well, you can hypothesize that the two lobes were joined together in a kind of collisional event, and these layers have been deformed by that event, because we have the evidence for deformed layer thanks to our observation and 3D modeling. And this might lead you in a hypothesize several scenarios for that event. So these are really a feedback that is coming to planetary science, starting from, let's say, geological modeling. So something that geologists normally do, and you can end up with something very interesting for the understanding of the processes involved in the generation of that body you are modeling. Okay, so I think we can probably stop here. We have some example. I can do it very fast, and then we can probably stop. So we tried, within the PlanMark project, we tried to apply test techniques in many different places, in different surfaces, planetary surfaces. And of course, what I can say to you is not easy. It's not like we have a lot of data. We have a lot of information we can use, and there is especially a problem where the data are very high resolution or a very low resolution, and maybe there is nothing in between, and you don't know how to merge that kind of data. It's very difficult. So the simplest example is data from this GPR data. I show you a slide before, but I didn't give you any details. So the idea here is that there was an rover running on the moon. That's a Chinese rover, and it performed this kind of path on the surface. It was collecting data about the subsurface using ground penetrating radar. So using electromagnetic waves to probe the subsurface. And basically the output of that analysis is something like this, right? So you can take this information, process it. You need to do a little bit of pre-processing. You need to digitize all your data, have everything in your computer. You need, of course, to couple the data with the navigation data, so to know where the rover was at which time. And of course, at the very end, you end up with a very nice three-dimensional representation. You can use simple models like saying, okay, I will represent my horizon in the subsurface as just planes, or you can use more complex models like saying, I will use a high-hand interpolator, like in this case, an RBF interpolator. But of course, the principles are the same. So you can basically have some data points in space, and you can fit those with your models. Now, an interesting point here is that you probably doesn't need much complex software to do that. You don't need to buy pricey software for 3D modeling for doing that. You can probably do everything with just QGIS, for example, because it's totally feasible to interpolate some surfaces in QGIS and then export them in a good format that is good for 3D visualization. So another case we will see later in the practical is the one with charade radograms. I already told you something about that. But the idea here is that you, of course, need to perform your interpretation basically on two-dimensional data. And when you have your interpretation, you can put all your data and information together to try to generate a representation of that interpretation. And this might be very useful because it might lead you to understand whether you made mistakes in your interpretation, whether the interpretation you made is consistent in all the places. So this is an example Riccardo have been working on, which is very nice because it basically there are this folded stratigraphic sequence. So for the non-geologists, those are called the axial planes of the faults. And there is, of course, a large work done on mapping. And as we said before, whatever you are going to map, it really depends on the topic you are dealing with. So in this case, they mapped each different stratigraphic horizon they could see, right? But that would not be something that you normally do for creating, let's say, a geological map. And also in this case, you can create geological section, and you can then import them in some software, like in this case, 3D Move. You can import all the section, and at the very end, you can create and generate the 3D model of your surfaces. So this is the last slide, and then we can have some question if we have time. And the idea of this slide is just to leave you a little bit of information on some software that I found pretty useful in the past, and also some that I'm pretty sure they will be useful as GemPy. They are developing it very nicely. They are improving it. It's a software to create three-dimensional geological modeling. It's totally open source, so have a look at that. Of course, it doesn't have a very nice interface like many open source software, but if you are good with programming, that is the way to go. And we have several general mesh handling software like Cloud Compare, MeshLab, Blender, and you can find many different of those. By the way, I'm just listing open source software because I really believe for many of the applications you might be dealing with, it's more than enough. And of course, we have VTKey, which is a C++ library for visualization. In ParaView, that is a very, very interesting software for anybody working with 3D data. It comes from, I guess, from what could be the particle physics field, something like that, from laboratories dealing with a huge amount of three-dimensional data. And it's very easy to use. And of course, you have QGIS. There are some functions to create 3D models, some function for interpolating surfaces. You can explore that. Of course, QGIS is well documented, and there is a large community supporting the documentation. So just look around and Google around. And then, of course, there are softwares that you might be interested in because they allow you to, they make it possible to create 3D models from pictures. So let's say photogrammetry and shape from shadows. Of course, the king is the stereo pipeline, but it's a little bit difficult to use if you just want to play around with 3D models and let's say take some pictures with your phone and create a 3D model. You can have a look at Mushroom, which is open also, and it's very easy. So I would like to end the talk here. And of course, we are happy to have questions.
Thank you, Luca. So if there are some questions, please keep
Working with stereos, is there any way to combine texture and 3D very accurate? Yes, of course, there are ways, but are pretty complex. And the point here is that if you are working with, it really depends. I mean, it depends if you are getting the 3D model out of the images you want to use as texture, that is a little bit easier. Instead, if you have a 3D model and some pictures that are just laying around and you want to put them on the 3D model, that might be more difficult to do. Of course, the idea is that you really need all the camera parameters for your pictures to know where the camera were pointing when, in respect to the 3D model you are trying to stitch your images on. To do so, I mean, the keyword is again bundle adjustment. You need to try to figure out a way to find very precise positioning and orientation in respect to the 3D model of your cameras. That's the only sane way of doing that. Of course, there is techniques called resection, if I'm not wrong, resection, something like that, which basically with a limited set of points, you can handpick them. So let's say you pick 12 points on your texture and 12 points or something like that on the 3D model, that they should be match each other, and you can try to compute back the parameters for your camera, basically the orientation, the rotation, and possibly focal length or something like that. Of course, there are toolkits to do that. Like, of course, there are something in MATLAB. There is a lot of work done in, especially, let's say, C++, high level, let's say, pretty complex level languages to use. But
also in stereo pipeline, there is a tool where you can put ground control points, and you can bundle adjust your image to the stereo pair. For example, if you want to register a new images on top of a DTM created from stereo pairs, you have, of course, to bundle adjust before, so you have to know the navigation kernels of the camera, the pointing, and so on. And then you can basically hand pick your ground control points on the same geologic features and apply a non-rigid deformation to the image that is then draped precisely on top of DTM. But again, it's not an easy task, as Luca said.
Yeah. I mean, they are doing some of this stuff a lot in whoever works on robot navigation. So there are many toolkits. I would suggest to have a look at OpenCV, which is a toolkit for computer vision that implements most of these algorithms. But if you are looking for something simpler, like a nice interface, there are, of course, commercial software. I cannot remember which one implements these kind of features, but there are commercial software that you can use to handpick some points and put your images on the 3D model. So Gianluca is asking whether we know about some software that we could use to create DAMs using photoclinometry and shapeform shading. Maybe you, Riccardo, know something about that.
Yeah, I can answer on that. So the answer is it's not an easy answer because, for example, there are also commercial softwares, or for example, also Micmac, Mushroom, all the softwares dealing with photogrammetry that can be used to reconstruct the surface. So you can basically feed all your images of Europa and then try to, there is also Pix4D, for example, but the problem is that none of these softwares are able to read the SPICE kernel of the images. This means that they do not know any parameter of the camera, not the pointing, not the navigation kernel. They don't know the for example, the aperture and so on. So what we will end up with is a 3D model that looks nice, but it doesn't preserve, let's say, correct information about topography, because it's only based on features matching on the image. It doesn't have any, let's say, intrinsic parameter of the camera, or not even extrinsic. In stereo pipeline, if you want to try and create TEM for example, icy satellites, I think is the way to go, because it now implements robustly the shapeform shading, is very, very heavily computationally speaking, and it requires fine tuning. And to my knowledge, I also worked on Galileo images on Europa and Ganymede that are few places where you have overlapping images with enough resolution and also enough baseline, meaning the separation of the two images in terms of observation angles and overlap, that are good to try and reconstruct the surface. Of course, what you can do is try to do that and also refine the images with the shape from shading. This is the way I will go with. All other softwares that have this shape from shading refining algorithm are to my knowledge, commercial softwares. Like, for example, I know that Envy has a module to do that, and also to reconstruct topography, but I am not completely sure that it can handle the navigation kernels of the image. Other softwares could have the possibility to hand pick and hand put inside the cameras the characters of the observations. For example, probably this can be done into Metashape, but I'm not completely sure. So in my opinion, the best way to do things is it also integrated seamlessly inside the ISIS pipeline that reads the raw data and then it transforms into cubes. So you can attach your navigation kernels. I would try to stick with in stereo pipeline. Of course, the key is just to detect the best stereo pairs you can have with the proper resolution and separation. And you can do that by using the pilot website that they explained you on the first day. It has a tool that can help you in evaluating which are the best suitable overlapping stereo pairs. It's just in the menu. If you just navigate into pilot, there's a, I can also show you if you want. Let me see. That can help you in detect which are the best stereo pairs.